So for today's lesson, we are going to start to switch gears a bit, and we're going to start to sketch and graph sine, cos, and tan. So we're going to also make sure we have an understanding of where do these curves come from. So I'm going to just zoom in here so we can look at this. So we're going to begin by graphing sine of x. Couple of things that we can recall. We know that sine is opposite over hypotenuse. And when we think of our opposite side, we were talking a lot lately about that's our vertical, right? That's our y value. So our sine is opposite over hypotenuse. So we are going to unravel, I like to call it, this unit circle, and we're going to find out what that looks like as a curve. Okay, so we are going to use our special triangles, and we are going to look at this curve and how we can sketch that. But before we do that, I want you to think about a few things. So I want to take us through. If we start, so this is our x value and this is our y value. So really I've just created a table of values and I've turned it sideways. My y value for that second row there is just the exact value, and then the one below is just the y value of an approximate. Okay, so really this is our table of values. It represents x, and then our y value is whatever sine x is. And we're going to look at these in radians. So when we look at this, if I look at what x is 0, so I know when x is 0, that's going to be on my positive x-axis because that's my angle 0. And what I can think about is what is the opposite side here. I have no height, right? My opposite side is 0 because I have not moved up or down off of that positive x-axis. So my exact value here, my height, is going to be 0. The value of that angle is of sine 0 is 0. And what we're going to notice is we're going to continue to rotate around that unit circle. So now if I rotate, I have an angle of pi by 6. Across from my smallest angle is my smallest side length in my special triangle. Sine is opposite over hypotenuse. So my exact value will be 1/2. I'm going to continue to rotate. And I'm going to rotate to my pi by 3 angle. Across from my pi by 3 is root 3, and my hypotenuse is 2. And then I'm going to continue to rotate, and now I'm at my pi by 2 angle. Sine of pi by 2. When I'm on my positive y-axis, I notice I have an opposite side of 1. My adjacent would be 0 because I have not moved left or right off of that axis. My opposite side is 1. My hypotenuse would be 1 if you were, for those of you who like to think about that imaginary triangle. So when I take sine of pi by 2, I get a y value of 1. And now I'm going to continue to rotate around my unit circle. And now my next angle is a 2 pi by 3. So I'm going to use my related acute angle. Across from my pi by 3 is a root 3 over 2. And I'm going to pause us there for a moment because I want you to notice something. What we have been doing is, you notice here sine has a height of 0. Our opposite side, that height is getting longer and longer as we rotate until we reach our maximum height at 1. And then we start to decrease again in height. And we're going to continue to do that as we unravel. So we're going to eventually, we've hit our maximum height. We're going to continue to go around that unit circle using our special triangles, and we'll eventually hit a minimum height, and then we'll continue to rotate around. So I'm going to give you a bit of time to do that now, and then we are also going to sketch this afterwards. So if we were to write these values, so once you have your exact values, we can use our approximates to help us with sketching afterwards. So I'm going to give you a bit of time to work through that. So now that you've had some time to work through it, let's continue on and see where we got to with this. So as we continue to rotate our 5 pi by 6, we get a value of 1/2. And then at pi, our opposite side, is back to 0. And now we've rotated into quadrant 3, and we start to get negative values because we know sine is negative in the third quadrant. We then rotate to 3 pi by 2, where our opposite side is a -1. It's the longest that our opposite side gets in our negative y-axis, so that becomes our minimum value. And then we continue to rotate back up to 2 pi, so that opposite side, our height, starts to get smaller. Perfect. Okay, so now let's just write those out as our approximates. And then our next step will be to sketch them. Okay. So I'm just going to move this up so we can see all of that. Oops. So let's first start by sketching from 0 to 2 pi. And what you'll notice in all the grids that I've provided you with is I will be asking you to, if you're given a grid, I'm asking you to graph between 0 and 2 pi. And there should be a negative here. Yes, perfect. Thank you. Okay. So if we're looking at our graph, we have our sine at 0 is 0, 0. Each of these grid lines is pi by 6. So again, this is what your grid will be that I provide to you. It will be between 0 and 2 pi with grid lines of pi by 6. If you notice where our scale is, each of those vertical grid lines in this example are at 0.2. So I am going to continue. So at pi by 6, I'm at 0.5. At pi by 3, I'm at 0.87. And I reach my maximum at pi by 2. So my opposite side is the longest at pi by 2. And then as I continue to rotate around that unit circle, that height, my opposite side gets smaller and smaller and smaller. And then I can continue to rotate. My height starts to get a bit bigger, but we've now entered into quadrant 3 until we reach 3 pi by 2, where we're at a value of -1, where our opposite side becomes the longest again, but so that provides us with our minimum, our most negative value. And then I can draw my curve through that. Perfect. And so there is our sine curve. From all of those points on our sine curve, what values do I want you to include for me? So I'm just going to zoom in here for us. When you go to graph these, when you practice graphing these today, We are eventually going to move on Monday into just sketching these. So for sine and cos, I'm going to remove the grid from you. Okay. For tan and our reciprocal functions, you will have that grid provided. For today's work, as we review our sine, cos, and tan curves, you will have a grid that you're going to use. On Monday, I'm going to remove that grid and we're going to fully sketch these. But when we go to graph these on our grid, what do I need from you? I need your max, your min, and your zeros. Your zeros being your x-intercepts. So what I want to see plotted from you are these 5 key points. So my 0, so these are my zeros, my x-intercepts, my max, and my min. Okay, so those are the key points that you will use to sketch. Couple of things. I'm hoping maybe if I say the word amplitude, you start to go like, oh yeah, right, I remember we talked about something to do with amplitude. The amplitude of our sine curve is 1. The amplitude is half the height. So you'll notice the height of our curve spans from 1 all the way to -1. So really it spans 2 full units. However, our amplitude is half that height. So half height provides us with an amplitude of 1. Another way we can also think about this, so when you're trying to come up with your sine curve, something else that you can remind yourself of. From 0 to pi by 2, that's going to represent quadrant 1. I know sine, my opposite side, is positive in quadrant 1. I know at pi by 2 it reaches its maximum. And then I know, it's also positive in quadrant 2, but it starts to rotate back down to where its opposite side is 0. As I rotate into quadrant 3, I start to have negative y values, which means in quadrant 3, my opposite side will be negative. I reach my lowest point on my curve. And then in quadrant 4, I start to rotate back up. That height starts to become smaller and smaller and smaller. And again, I keep referring to height here because I'm dealing with sine, which deals with our opposite side representing that height, those y values. Awesome. How long does it take for us to do one full rotation here? 2 pi units. Okay, so we call that the period of this function is 2 pi. So how long does it take for one cycle to occur? It requires 2 pi units for our base sine curve for that to occur. You'll notice at the bottom I have continued the graph of y equals sine x for the domain of -2 pi to 2 pi. So we're going to have a negative rotation here as well. What I want you to think about, that just means we've dropped our terminal arm through the 4th quadrant. So if we started at 0, where we have a height of 0, if I rotate that, my height gets larger, larger, larger. That opposite side's getting larger and larger until that opposite side is at a -1. My opposite side, that height, starts to get smaller, 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 smaller until it is at a height of 0. It's now should be positive y values. That height starts to get, that opposite side starts to get bigger, 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 bigger until I reach my maximum. And then that height, which is At its highest point, that height starts to get smaller, 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 and smaller, right? We can tell our height here on those points around our circle would start to get smaller, smaller, and smaller. So as you can recall from last year as well, we know that our sine curve is a periodic function. It will repeat at the same y values at regular intervals. So that is our sine curve. Again, you need to be aware and understand your base sine curve. Its key points, its 0, its max, and its min, and when those occur. So now when we go to look at our cos curve, we should be thinking to ourselves, cos is adjacent over hypotenuse. So what is happening to my adjacent side? So again, I've just turned my table of values. My x value and then my y value would be the exact value of cos x. So in this case, I have x and whatever cos x is. That provides me with my y coordinate here. So if we think about the same idea that we did on the last one, but now we're following our adjacent side. So what is happening to that adjacent side? So when I start at 0, my adjacent side, we should be noticing my adjacent side is at 1. It is the largest possible adjacent side that I have. As I start to rotate, I rotate to pi by 6. I should notice that my adjacent side is smaller than what it was there in orange, right? As I rotate, that adjacent side is getting smaller. So my adjacent side at pi by 6 is root 3 over 2. I continue to rotate. At pi by 3, if you notice, my adjacent side is getting smaller. My adjacent side for cos, so cos of pi by 3 is 1/2. And then when I get to pi by 2, we notice my adjacent side is at 0. It has not come off of that vertical axis. And then we can continue to rotate. Well, when I go to 2 pi by 3, I have an adjacent side again. It's starting to get a little bit bigger. But I know cos is now onto negative x values, right? That adjacent side is now a negative 1/2. I rotate to 5 pi by 6. We notice my adjacent side is starting to get larger. I'm still on the negative x-axis, so my value of cos is negative. And then as I rotate to pi, I am lying on the negative x-axis. So my adjacent side is a negative 1. So I would like you to take just a couple of minutes to continue on and fill in the remainder of that unit circle. You can write our values as our approximates, and then you can work to graph that. So let's see how we did here. So we can continue to rotate on that unit circle. And we should start to get that then our adjacent side was at negative 1, so that's going to be our minimum value. And now we have to start to, our adjacent side starts to get smaller and smaller. And at 3 pi by 2 on that negative y-axis, our adjacent side is at 0. And so now it has to start to get a bit bigger. Our adjacent side now is on our positive x-axis. And so again, really all we're doing is thinking about what those special triangles are. So there's a few ways you can look at this. I've drawn on those special triangles to try to show you the relationship and how that adjacent side gets smaller and then gets bigger. You also can look at your special triangles just to help you calculate that at each of those angles. Okay, so now let's just work to graph this. So we notice because we start on our positive x-axis, our adjacent side is at 1. So we start our cos curve at our maximum. Again, you'll notice the scale is 0 to 2 pi with each of those grid lines being a pi by 6. As we start to rotate, our adjacent side gets smaller until we're at pi by 2, where that adjacent side is 0. And then we continue to rotate, and it gets larger. And then at pi, we're at -1. So we continue to rotate. And again, we end at our maximum because our cos curve is periodic. Okay. So let's combine to give a smooth curve. Ooh, I do not like the end of that. Awesome. So again, if we were to zoom in on this a bit, what are your key points of your cos curve? Well, cos, we know, starts at its maximum and it falls. Sine started at its 0 and it rose. Cos starts at its maximum and it falls. So we go max to a 0 to our minimum, back to a 0, and we finish at that maximum. So those are the key points. Again, minimum, maximums, and zeros for all of these curves. I showed you on our last example how you could take your unit circle, you could drop your terminal arm and rotate clockwise to come up with that negative rotation. On this one, I'm going to remind you that it's periodic. So again, we know that if the period of cos is 2 pi, well then it has to repeat at the same y values at regular intervals. So I can take those points and I can just rotate each of them back to pi, and that is another way that I can get the rest of my values. Perfect. Please double check the curvature of your graph. You'll notice that mine doesn't peak. It doesn't become like triangles at it, right? It's a smooth curve, and you can notice just the slight changes of my curvature as I go through each of those quadrants. So again, cos is positive in quadrant 1. We notice we have positive y values. Cos is negative in quadrant 2 and in quadrant 3, so we have negative y values in those quadrants. And it is positive in quadrant 4 because it has positive x values. Its adjacent side is positive. You'll notice our amplitude of our cos curve is also 1. Half that height is 1. And the period of this function is 2 pi. So it takes 2 pi units to go through a full rotation. So for our tan curve, I'm going to have you think about it in a couple of different ways to see which way helps with your understanding. So if we were to come up with these values, I want you to think about tan is opposite over adjacent. So if I were to start, so again, I just have turned my table of values, so now I'm saying x and tan x. So my y value is that value of tan x. So if I have my opposite side over my adjacent side, my y over my x. If I start at 0, where we start all of our rotations at 0, I'm on the positive x-axis. My opposite side is 0. My adjacent side is 1, right? So opposite over adjacent, that gives me a value of 0. If I start to rotate, so if I rotate to pi by 6, you'll notice my opposite side is starting to get a bit bigger. My adjacent side is starting to get a bit smaller. So my number on top is getting bigger. My number on the bottom is getting smaller. So you'll notice we're starting to have a slightly bigger number. And then if I rotate more, same thing. My height is getting bigger. My adjacent side is getting smaller. So I'm going to have a slightly bigger number. Okay? So that's how I just want you to think about it. Where does it come from? For the majority of us right now, what we're probably going to do is we're probably going to draw out our pi by 6 triangle and just go, okay, pi by 6 is 1 over root 3. And then when you type that into your calculator, you're going to find out the approximate value is 0.58. And then you're probably going to go to your pi by 3 triangle and go, tan of pi by 3 is root 3, which will give me a value of 1.73. Right? So I wanted to talk to you about this visual so you can see what's happening. Our opposite side is getting bigger, our adjacent side is getting smaller, which means I'm getting a larger value. At pi by 2, something interesting happens here. Our opposite side is at 1. Our adjacent side is at 0. So opposite over adjacent gives me 1 over 0, which should be kind of ringing a bell like, I can't divide by 0. So that is undefined. It is undefined at pi by 2. How do we represent something that's undefined? Well, if you think back to some of the graphs that you've just done recently, we have a vertical asymptote here for where that is undefined. So our tan curve actually has asymptotes in it. Because at pi by 2, its opposite side is 1, its adjacent side is 0. We cannot have 0 in our denominator. It is undefined, so we need to represent that as that break or discontinuity in our graph, and we can represent that using our asymptote. Okay, so that's just one of the things that makes tan a bit different. Well, then let's continue to rotate. We know that 2 pi by 3 is just now in our second quadrant. And tan is negative in that second quadrant. So I'm going to be at a negative root 3. And I can continue to work along my unit circle to unravel all of those values. So now I'm at a 5 pi by 6. And that's going to give me a negative 1 over root 3. And then when I get to pi, My opposite side is 0. My adjacent side is a -1. So 0 over -1 is just going to be 0. So I want you to take a minute or two, draw. I think for tan, it's probably easier if you're looking at drawing each of those special triangles instead of trying to take into account each time what's happening with my opposite side, what's happening with my adjacent side. But I wanted you to be aware of that so we can be mindful of, should it be getting bigger or should it be getting smaller at this point? So take a couple of minutes, fill in the rest of that table, and then we will get sketching. Okay, so let's see how we did here. So we have 7 pi by 6. We are now in quadrant 3, which should provide us with positive values. Tan of 4 pi by 3, so when you draw that special triangle. And then we get to 3 pi by 2, where our opposite side is a -1, and our adjacent side is 0. So again, we're back to this -1 over 0. So we know that that's going to be undefined. And then I'm going to continue into the 4th quadrant. 5 pi by 3. Opposite over adjacent will give me a -√3. And then I can continue on. And then I'm back to 2 pi, which should give me the same value of what 0 did because it lies on the same terminal arm. Awesome. So a few things we need to just talk about. And then we'll get to our sketch. I'm just going to clean this up a little. So, are there any interesting values on our tan curve? My guess is we should be going, yes, there is. You just told me there was asymptotes, right? So yes, there are some interesting values. Those interesting values occur at pi by 2 and 3 pi by 2. Because at those points, our curve for tan is undefined. And we can represent that those points do not exist by the use of asymptotes. So if I'm starting at 0, 0. You'll notice the y-axis, the scale, I've changed the y-axis here. Again, you'll notice the x-axis still 0 to 2 pi, each grid representing a pi by 6. That will not change. So I have my points. At pi by 2, I'm going to use my straight edge and draw an asymptote. At 2 pi by 3, I'm going to be at -1.73. And I'm just going to continue on. At pi, I know I'm at 0, and I'm going to continue to plot these points, which you are all capable of doing. At 3 pi by 2, I notice again, using my straight edge, I'm going to draw on that asymptote. And then I'm going to continue on with plotting those points, and I notice that, oh, those y values repeat at regular intervals. So now that I've used the values above, I'll just zoom in here so we can really see what's happening. So we know that our curves continue to get closer and closer to a vertical asymptote. We also know that they do not cross vertical asymptotes. So that represents our curve for tan. However, so we have so many things to unpack here. So let's first start by unpacking what is the period of this curve. what you'll notice is I start at 0 for tan. I have this asymptote. And do you notice it takes me pi units before I repeat that same cycle again? Because if you notice, now that begins to repeat. So tan has a period of pi. It takes pi units for one rotation to occur before we see that repetition again of our y values that repeat at regular intervals. Another way that you can look at what does that look like, well, this would be, notice, one full rotation, then we get that next asymptote, and then we start to rotate again. Tan is periodic. It repeats at regular intervals. So the period of tan is pi. So if normally we have to sketch, and if I'm graphing and I'm saying to you, graph your zeros, your max, and your mins, you should have a problem with that for this curve. What do you notice that our tan curve does not have? Right, it does not have max and mins. That should be a problem to us, okay? First, we should be asking ourselves, why does it not have a max or a min, but sine and cos do? So I want you to think about that for a moment. What is different about the relationship of tan compared to sine and cos? Tan does not have a hypotenuse. We know the hypotenuse always has to be the longest side length, right? The hypotenuse in a triangle is the longest side length. So for our sine and our cos curves, if our hypotenuse has to be the longest side length, then it's always contained by that hypotenuse. So it has to have its maximum and its minimum. I can't have my opposite side being bigger than my hypotenuse. So what do I mean by that? If sine is our opposite side over our hypotenuse, and this hypotenuse always has to be the bigger number, the numerator divided by that bigger number will always be a value less than 1, unless when we're on that actual unit circle, right? Because it's contained by that hypotenuse. It's only when our numerator is bigger than our denominator that we will have a number that's bigger than 1. Is everybody okay with that? With tan, there's no max or min because the opposite and the adjacent side are independent of each other, right? This because the hypotenuse has to be the longest side. But for tan, no one's holding them back. Opposite side, adjacent side, it doesn't matter. They can just be independent and they're not held to that one of them has to be bigger than the other. But a hypotenuse has to be the longest side length. So there is no max or min on our tan curve. And this is because the opposite and adjacent sides are independent of each other. So as a result, we have no amplitude on our tan curve. So why is there no amplitude? Because amplitude's half our height, where we take our max minus our min divided by 2. We have no max and no min to subtract to divide by 2. Okay. Couple things. First, let's just finish off this graph. So you'll notice your asymptotes occur every pi units. So I can work backwards and I have pi units, which every pi units is 6 grid lines here, right? Because 2 pi units, and you'll notice we have 12 grid lines. And I can repeat. These repeat at regular intervals. So I can take those y values and I can have them repeat at regular intervals. So where this one was, and what you'll notice is where one part of our graph ends, the next part begins, right? And so what I mean by that, I'll highlight where this ends, this one begins. It's all periodic. Okay. The last piece I want to mention to you about tan is, I don't know about you, but I'd prefer not to keep in mind, okay, my pi by 6s are 1 over root 3s, and my pi by 3s are root 3s, okay? And then, okay, that's a 0.58, that's a 1.73. If you recall from tan, so why did I give those to you then? Because I wanted us to stay consistent with what that looks like when we unravel those unit circles. Okay, but I want you to think about good old special triangle of pi by 4. It has a 1, 1, root 2 triangle. Pi by 4. Can we agree that if this here is pi by 2, pi by 4 is half of that? So pi by 4 is going to be 1.5 grid lines. Tan of pi by 4 gives me a y value of 1. 3 pi by 4 gives me a y value of negative 1. So instead of working with your pi by 6s and your pi by 3s, on our tan curve, I'll do my curves this way, and I encourage you to do them as well, is I am going to use my key values. I need my zeros. But I am going to use my pi by 4 angles because that allows me to just have to work with y values of 1. And again, you'll notice I don't have to remember all of those points that I've just circled there because I've just circled points for 2 full rotations. As long as you know them for 1 full rotation, you're okay. So again, our first rotation would be 0, 0, pi by 4 and 1. And then we just know that curve is getting closer to our asymptote. I have an asymptote at pi by 2. At 3 pi by 4, I know in the second quadrant tan is negative, so it's going to be at a negative 1. And then I'm rotated back to my y value of 0. And that is 1 full rotation of tan that at that point you could just continue to repeat. So those are your 3 graphs, sine and cos. Again, today we're going to work on transforming them. We're going to transform tan as well, but on Monday we are going to start to remove the grid and draw sketches of sine and cos. Tan you will always have a grid for because this is the first time that you are working with tan. So that is your first lesson for today. The biggest piece on that is knowing what your key values are and what the shape of those grids, those curves look like.